Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussion. We've been discussing analysis of circuits containing capacitors and resistors and inductors. And last few lectures we were looking at analysis in the time domain. And today we look at an alternative way of understanding these circuits through what we call as sinusoidal steady state analysis. So the sinusoidal signals are, besides their usefulness in understanding and characterizing electrical systems, they are also widely present in many electrical systems. For example, we are all familiar that the power that we get at our outlet is a sinusoidal signal. So it's generated at a power plant and then through transmission lines and through further in between a step down and all that step down transformers is brought to our homes. So that power is sinusoidal in nature, right? And if we look at communication, for example, when we see antennas mounted on towers like this, and we look at the signals that are transmitted by these antennas and the signals that are received in our mobiles or in our television radios, those signals are also they're sinusoidal signals modulated by let's say a voice or a picture signal, but the backbone of that particular signal is a sinusoidal signal here. So it's a part of power that is generated and sent to our homes, is part of communication. So sinusoidal signals are of inherent interest to us. So that's why we need to analyze circuits when they're excited by sinusoidal signals. The other thing is, even if sinusoid is not of direct interest to us, any periodic signal, you've all learned the concept of Fourier series. A periodic signal can be expressed as sum of sinusoids. So let's say your interest is in a square wave, which goes from 1 to -1, a periodic square wave like this. It's easy to show through Fourier series that we can express it as a sum of sinusoids. In this case, we have taken, mathematically, the square wave signal can be expressed in this particular form here. So a sum of sinusoids, and in this case, I think we have taken a sum of 5 sinusoids, and the approximation to a square wave is reasonable. If we take more sinusoids, the approximation to a square wave becomes more and more accurate. If we look at a triangular wave here, if I try to approximate by a single sinusoid, obviously the approximation is not that good. But if I take 5 sinusoids, well, it becomes hard for you to distinguish which one is the real sinusoid and which one is the approximation. The approximation, as if you notice carefully, there are some variations in the red curve here. So that's the approximated triangular wave compared to the full original triangular wave. So the point is that these signals, even if they are not sinusoidal, we can express it as sum of sinusoids. And we've been talking of linear circuits. So note that if you have a sum of 5 sinusoids, and if you evaluate the response due to one sinusoid, each sinusoid individually, you can sum them up, and thereby you can get the final triangular wave response to the triangular wave. The sinusoids have also another interesting property, that their derivatives and integrals are sinusoids also. So if we take a derivative of sin x, we get cos x, which is nothing but sine with a 90-degree phase change here. The derivative and the integral of sine is also a cos with a minus sign, so again with some phase change here. So the importance of this is that when we excite circuits with a sinusoid, well, as the sinusoid goes through my circuit, if I have capacitors and inductors, the sinusoid may undergo a derivative or an integral. But what would happen is that as a result of that particular process, the signal would stay a sinusoid, with some phase difference, of course, but it would stay a sinusoid. And that makes analysis of circuits which are excited by sinusoids much easier as compared to, let's say, when we have some other signal here. So let me give you an example here. Okay. So let's say we have a circuit like this here. So we have a resistor, a capacitor, and a resistor and an inductor. And let's say we excite this circuit using a triangular wave here, right? So the input is a triangular wave. And when we look at the output here, at the capacitor output here, you can see that the capacitor output looks like some kind of a distorted maybe sinusoid. If I look at the output at the inductor here, so that looks like a exponential charging, discharging, and that kind of a sawtooth kind of a, but not a perfect sawtooth kind of a behavior here. So the point that we just made was that when you drive your circuit through a triangular wave, well, the signals everywhere in the circuit are not triangular anymore. Somewhere it is maybe closer to sinusoid, somewhere it may be closer to a sawtooth signal that you see here. And that makes analysis more difficult because you can't simply, if you want to, let's say, add up two signals, well, adding up a triangular and a sinusoid or subtracting a sawtooth kind of a signal from a sinusoid is not going to be easy. Remember that when we analyze circuits, we transform them into equations. And in equations, of course, when you're trying to solve, you have to add up quantities, you have to divide quantities, multiply them together. And then when each waveform, each signal is of a different form here, then performing that kind of an addition, multiplication, division, all that becomes difficult here. So analysis of a circuit through a triangular wave is not straightforward. But note what we just said, that we can take the triangular wave and break it up into a sum of sinusoids. So if we analyze this particular behavior due to each one of those sinusoids, and then we sum them up because it's a linear circuit, then we'll get back the result that we want here. And the advantage of sinusoidal analysis is that if I put here a sinusoid, so we'll see the same circuit here. So when I excite it through a sinusoid here, right, the voltage at the capacitor is also a sinusoid, the voltage at the inductor is also a sinusoid. Of course, with different phase relationships, okay, with different amplitudes and different phase relationships, but they're still sinusoids. So that makes analysis, that's what we are saying, that makes analysis of circuits using sinusoidal signals easier, because adding up two sinusoids or multiplying two sinusoids is much easier than adding up a triangular wave and a sawtooth wave. All right, and so even if your interest is not directly in sinusoids, because we can express any signal as sum of sinusoids, and we are talking about linear circuits, the analysis for sinusoidal excitation then becomes very, very important. Okay. All right, so before we go on and look at this into detail, we had talked about this particular circuit as an example, an RC circuit. And we said that when you switch on, either you close the switch or let's say at time t equal to 0, you switch on this particular voltage Vs from 0 to some value here, then the capacitor voltage has this kind of a behavior here. Now, we can break this behavior into two parts here. One is what we call as the steady state or the forced response. So the idea is that any circuit that you take, and when you switch on a voltage, then there would be a transient response. The circuit would take some time to settle down, and then there would be a steady state response. Right? In this case, for example, this is a constant voltage. Vs is a constant voltage. So when we excite this particular circuit through this voltage here by closing the switch, there is going to be a transient response. Transient response, which means that it would last for, as you can see here, after some time, this particular response will die down. It starts from 0, and then after a few time constants, this particular part will not be there. And the only thing that will be left with is steady state or forced response. Steady state or forced response meaning response of the circuit to a constant voltage that you applied here. And we know that if you apply a constant voltage here, then under steady state condition, the capacitor is an open circuit, and so the output is Vs here. So whenever we take a circuit and we excite it with some voltage source, there is going to be a transient response, and then the circuit would settle down to a forced response or a steady state response here, right? So this is what we can see in this particular one. There's a transient response, and this is a steady state response. So steady state response need not be, if we generalize the meaning of steady state need not mean that things are not varying with time. Steady state may mean that the pattern that we observe is kind of fixed. So let's look at that here. So in this case, we are same RC circuit, but we are applying a sinusoid. And when I'm applying a sinusoid here, so note the behavior that we get here. We get a behavior here, and then gradually it settles down to. So here also, what you can see is that there's a transient part here. There's a transient part. Initially, the output here, capacitor output is varying in some manner here, and gradually it settles down to its periodic fashion here. So this is what we call as the steady state part of the response here, right? So we have applied a voltage here, and the voltage has been applied for a long time, and the voltage is sinusoidal. So the pattern, the repeating pattern that you see here is now fixed here. While in this case, the circuit is still trying to come to the final steady state part here. So this is the transient part here. So we can talk about transient and steady state even when signals are time varying. Steady state is when now the pattern, right? We're not saying signal is not varying with time. Signal is obviously varying with time, but there's a pattern that you see here, and the pattern is now constant, is not changing with time here. While here, things are changing with time. All right, so that's what we mean by steady state and transient here. Let's look at this case. In this case, we applied a triangular wave here, and we applied a triangular wave as input. So let's look at the output here. So look at the output here, VC. So the output of the VC here is, you can clearly see that there's a transient part here, and then it settles down into this kind of a behavior here, right? So this is the part here which is steady state, and this is the part which is the transient part here, right? So this is in response to the triangular wave. Okay, so let's come to sinusoidal excitation. Okay, so when we excite a circuit with a sinusoidal signal here, the circuit will have, as you can see here, the red is the input here, V1. Red is the input here, and the output is shown in green. So when we excite the circuit with sinusoid, there would be a transient part here. You can see that initially the sinusoid, the output is here, then is here, and then is here, and then gradually it's settled down here. So there is a part here which is what we call as the steady state. And what we are interested in is, let's say, in analyzing circuits which are driven by sinusoids, but under steady state condition. We are looking at this particular condition, that the sinusoid has been applied for a long enough time. So we are not bothered about this initial part here, this initial transient part here, but we are looking at the steady state part here. So that's what we call as sinusoidal steady state. Okay, so the sinusoid has been applied. It has been applied for a long time, so that the circuit has settled down into its, sinusoid is a periodic signal, the circuit settles down into its periodic behavior. And this periodic behavior is what we are looking at here. So that's what we mean by sinusoidal steady state. Steady state does not mean here change, no change with respect to time. Steady state only means that now the pattern or the periodic signal is no longer changing. It has settled down into its well-defined periodicity. Okay, so we want to look at a behavior of circuits in response to sinusoids under steady state condition, and we would call that sinusoidal steady state analysis. Okay. All right, so we've been interested in linear systems. So let's say you have a linear system like this, and there's an input and an output here. And if you want to understand this linear system, there are various ways of understanding linear system. So if you want to understand this linear system, as an example, there could be an RC circuit, and you want to understand the output of the RC circuit here, let's say the capacitor voltage, when you apply some voltage here. One of the ways of understanding a linear system is you excite it with a sinusoid. You excite it with a sinusoid and you look at the response here. Okay, same thing here. You excite it with the sinusoid and you look at the response here. And what we do is we excite it with the sinusoid and we look at its response as a function of frequency of the sinusoid. Okay, so for example, we would apply a sinusoid, and note that in a linear circuit, the amplitude doesn't really matter. So we apply with the 1 volt and we'll get some output. If I want to make it 2 volt, the output will also double. If I make it 3, the output will also triple here. So the magnitude of this input, it doesn't really matter. I can put 0.1, I can put 1, anything here. So many times the convention is we put it as 1 cos omega t. So the idea is the linear system that you're trying to understand, what you can do is you can excite it by a sinusoid like this here, and then observe the behavior of the, so output is also going to be a sinusoid. We said that as a sinusoidal signal goes through your linear system, it will undergo maybe a derivative or an integral and things like that, but it would stay as a sinusoid. So the output is also going to be a sinusoid, except that it will have some magnitude and it will have some phase with respect to this one here. So what we can do is we can study this particular system where we look at the amplitude of the output as a function of frequency, and we look at the phase of the output as a function of frequency. So the output is going to be like this here in general, with some A0 amplitude, will be omega. It will depend on omega. Different frequencies will have different consequences, and the system will behave differently. And so it's going to be a cosine signal also at the output, but with some phase difference here. So the characteristics of this linear system is defined by A0 omega and theta omega. The amplitude as a function of omega and theta as a function of omega. And we are not justifying it mathematically or rigorously here, but what we are saying is in a linear system, if you know A0 as a function of omega for all omegas and theta as a function of all omegas, you know everything about the linear system. The linear system is fully characterized. So A theta and A0 omega and theta omega determine the complete characteristics of the system, right? So this is an alternative way of, you could also understand the system not through sinusoidally, but for example by applying a step voltage going from 0 to 1 volt and then looking at the response, the transient response. You can also characterize it by that means. But sinusoidal, steady state sinusoidal analysis makes us analysis easier, and not only that, makes us understand the system and helps us in understanding and designing systems to meet a particular set of specifications. All right, so any linear system that you're wanting to understand, what you could do is excite it sinusoidally and then look at the response of the output in terms of its magnitude and phase as a function of omega. So for example, this circuit that we have been talking about, RC circuit here, and our interest is in, let's say, the output voltage here, voltage across the capacitor. So what we do is, if you want to understand this particular circuit, excite it using a sinusoid, right? And what we take amplitude as 1 cos omega t, and then you study the output here. So here output will be of this kind, but we study output as a function of omega. So right now I'm not deriving it, but I'm showing you what the output is going to be. A0 as a function of omega. So note that omega is 2 pi f. F is the frequency. So frequency we are varying here from 10 hertz up to 1 megahertz here. And because you want to, the system is fully characterized when you look at the amplitude over a wide range of omega. Okay, so a wide range of omega. So that's why we are plotting frequency on a log scale here. Otherwise, you won't be able to see the entire behavior. When you have such a large range of variables, it's best to plot them on a log scale here. So we look at the output here. So the output A0 omega, note that it goes like this here. Right, so it shows that if I have low frequency signal, let's say 10 hertz, then the 10 hertz sinusoid is able to just pass through this particular circuit and appear as 1 volt here. So 1 volt signal of 10 hertz frequency will appear at the output as of 1 volt with 10 hertz, right? So circuit is like transparent to low frequency signals here. But if you have a 100k signal here, 100 kilohertz signal here, so you may apply a 1 volt cos with the frequency of 100 kilohertz. Well, at the output, what do we see? At the output, we see almost negligible, 0. So the circuit has almost rejected that high frequency component 100 kilohertz here and 1 megahertz also here. So that's why we call a circuit like this. It helps us understand that this circuit is acting like a low pass filter. It is passing the low frequencies. Low frequencies are passing easily through this particular circuit here, but high frequencies, 100k, 1 megahertz, even 10 kilohertz, they are getting severely attenuated and they are not passing. So note that by analyzing this particular circuit, through the sinusoidal steady state analysis, we are able to understand what this particular circuit really does. In the time domain, we could see that the circuit was charging. When we apply a step voltage, it was charging towards a constant value, and when we remove the voltage here, it would discharge. But this one is providing us with additional insight that this circuit acts like a low-pass filter here. And the phase value, if you go and look at the other part is the phase value. The phase value starts from 0 and then eventually goes towards 90-degree phase here, right? So the signal that comes out initially for very low frequencies, the phase is also not, phase is very close to 0. So the signal, as we said, the circuit is transparent to low frequency signals. The signal that you apply here just appears over here. But as the frequency increases, the amplitude also decreases, and the phase also starts to get, starts getting different here. The phase starts becoming negative here. Okay, so what we are saying is you can understand linear circuits. In fact, you can obtain complete information about a linear circuit if you excite them through a sinusoid. And you look at the magnitude of the output voltage as a function of sinusoid, and you look at the phase as a function of sinusoid, and you'll be able to get understand that particular circuit, what its function is, and then that would help you understand and then design those particular circuits for different applications that are there. Okay, so that's what we are trying to do here. This circuit can be understood in terms of A0 omega and theta omega here. So that's what we mean by sinusoidal steady state analysis. Excite the circuit through a sinusoid and look at the output. The output could be voltage here. It could have been current through the resistor. Then we would have looked at current as a function of omega, and the phase of that current, magnitude of the current as a function of omega, and the phase of the current as a function of omega. And as a function of omega, and take omega as large a range as possible. Note that beyond 100K and 1 megahertz, we can even go to 1 gigahertz, but it's not giving us any additional information. It's practically fallen to 0 here. And similarly, we can go to 1 hertz and all that. We know what the behavior with 1 hertz is going to be, is flat here. So you can choose a frequency range which will illustrate what the behavior of that particular circuit is. And then look at both the amplitude and the phase part here. Okay, so we are seeing the importance of sinusoidal voltages and currents. So let's become a little bit more familiar with these. These things are trivial, but sometimes it's good to refresh our memory here. So we're talking about a sinusoidal signal which has an amplitude, and we'll describe a signal in terms of cos here, Vm cos omega t, and then there is a phase theta here. So Vm is the peak value, omega is what we call as the angular frequency in radians per second, right? So all of you are familiar with this polar plot. You can imagine this this signal as the projection along x-axis of a vector here, which is rotating with the frequency of omega here, right? So that's t is the time period, f is the frequency here, and we know that omega equal to 2 pi by t, omega equal to 2 pi f. We write it like this, and theta is the phase angle, right? So this is the signal with which we'll be dealing with. Sinusoidal signal expressed as an amplitude in terms of cosine. We can write in terms of sine also, but we'll write it in terms of cosine and with some phase value theta here. Okay, so very simple. What is the amplitude, phase, angular frequency, time period, and all that for this signal here? So now when we write a signal like this, note that our representation is, we would like to represent it everything like this here. So phase will be determined from here with this kind of a representation, okay? So we would like to recast the sign in terms of cos here, right? So this is our representation of a sinusoidal signal here. So we know that sine and cos are related like this here. So we can write our this signal here, 5 sine 4 pi t minus 60 in terms of Vt equal to 5 cos 4 pi t minus 60 minus 90 here. So we cast it in this particular form. And then the amplitude is 5. We just compare amplitude is 5 and phase is minus 60 minus 90 is minus 150 degree. Phase of the signal. Phase in radians, all of you know 360 degrees 2 pi. So phase you can convert it into radians. And frequency is omega is 4 pi here. And we can omega is 2 pi by t. So we can get t equal to 0.5 second here. And frequency is 2 hertz here, right? So that's these are simple things. But keep in mind that this is our representation, default representation of signal here. So we would like to represent all signals finally in the form of Vm cos omega t plus theta. So phase will be with respect to this representation. Okay. So if somebody asks, let's say, find the phase difference between these two currents. I1 is 4 sine so much, I2 is minus 5 cos 377 t minus 40 degree. So to do that, what we do is each one of them, we first convert it into our standard representation. This is a standard representation. So each one of them, we convert it here. So I1 will become 4 cos so much plus 25 minus 90. I2 is minus 5 here. So theta 1 is, for this theta 1 is minus 65. I2 is here. So we convert it again in a cos. We don't leave a minus sign here. All minuses and all that are put into the phase part here. So we write it as 5 cos 370 minus 40 plus 180 degree. Cos 180 plus theta is, all of you know, cos 180 plus theta is minus cos theta and all that. So those relationships we use. So this one, theta is 140 degree. Right, so what is the phase difference? Theta 1 minus theta 2. Theta 1 minus theta is minus 205 degree. And when we specify phase difference, we usually do that between 180 and minus 180 and 180. So we can add 180 here, and we say theta 1 minus theta 2 is minus 25 degrees here. Okay, you just transform it into the phase, so transform it into minus 180 and 180 degree here. So we'll come back if there's a how do you specify the phase difference a little later on. Okay, so let's continue our discussions related to sinusoidal steady state analysis. So we've said that the sinusoidal steady state analysis is of interest to us because it helps us understand the system. The analysis is because all the signals stay sinusoids, the analysis is easier here. So we'll look at how, let's look at in more detail as to how we can carry out the sinusoidal steady state analysis here. So we start a discussion with linear system. So if it's a linear system, let's say this is the input and this is the output here. If I apply x1t, let's say a signal x1t, and let's say the output is y1t, fine. Now, because it's linear system, you know that if I multiply x1t by a, just scale it by a, make it twice as large or half as small and things like that, the output is also going to scale like this, a into y1t, right? So that's because of the linearity here, so scaling property it obeys. Okay, so let's say we apply a signal x2t. Well, if I apply a signal x2t, let's say the output is y2t, obviously the different signal and a different output. But what does linearity really mean? Linearity means that suppose I know the response to x1, which is y1. I know the response to x2, which is y2. Suppose I applied a signal here, one single signal, which was a1 x1 plus a2 x2. What will be the response to the output? Well, because it's linear, I already know what is the response to x1, which is y1. I already know what is the response to x2, which is y2. So if you apply this signal, I know the response will be a1 y1 plus a2 y2. Right, so that's the property of a linear system. It obeys superposition. If the signal is a superposition addition of two signals here, and you know the response due to x1, you know the response due to x2, well, you can easily compute the response due to the composite signal here will be a1 y1 plus a2 y2. Right, so that's a property of linear system, that it obeys superposition principle. All right, let's see how we can use this particular property to help us analyze linear. So our linear circuit is nothing but a linear system. So a linear circuit in response to sinusoidal signal here. All right. So let's say my x1t is a cos omega t plus theta. Right. So we apply our signal, which is a cosine signal, sinusoidal signal. And let's say the output is y1t, whatever it is. And we've been saying that as a sinusoidal signal goes in, the response is also going to be sinusoidal, but let's not worry about it too much right now. Let's say it's y1t. Let's apply a signal x2t, which is a sine omega t plus theta. Let's say the response is y2t. Okay. Now note that it's a linear system, right? So suppose now I apply, and suppose you know y1 and y2. Suppose you now apply xt equal to x1t plus j times x2t. J is a constant. What is the output going to be? Well, the output is going to be y1t plus j times y2t, right? We just learned about superposition principle. So the yt will be x1 will result in y1, and j times x2 will result in j times y2 here. Okay. Now let's say j is a constant, but let's say j is square root minus 1 is the imaginary quantity here, right? So let's say j is equal to square root minus 1. Then xt can become, note that xt is x1t, which is a cos omega t plus theta, plus j, a sin omega t plus theta. So xt can be written as a e to the power j theta into e to the power j omega t. So we've used this identity, Euler's identity, e to the power j omega t is cos omega t plus j sin omega t. So if we say that j is equal to square root minus 1, then xt becomes a e to the power j theta into e to the power j omega t, right? So that's the signal that we have applied, the superposition of these two signals with the j square root minus 1. So that's the signal that we have applied. Well, what is, so if we apply, of course, we'll get some yt here, right? So in response, I would have yt, which is equal to y1t plus j times y2t. But let's say your interest was in y1. Your interest is in y1 and in response to x1, right? But then, so your interest is that given x1, what is y1? But suppose we find out that given xt like this here, given xt like this, suppose we find out yt. All right, suppose it were easier for me that if I apply xt like this and I find yt, what will be y1? Well, y1 will be real part of yt here. Note that this relationship yt equal to y1t plus j times y2t, j is the imaginary quantity, so the real part of yt will be nothing but y1t here. So the idea is as follows. The idea is you are actually interested in the response of the circuit to x1. Response of the circuit to x1. But what we are saying is, suppose you find the response of the circuit to xt. And xt is not x1t plus jx2t. So if you find out the response to xt, which will be yt here, which is y1t plus jy2t here, right? So suppose you're able to find out yt, then the response to x1 would be nothing but the real part of yt. Now, why are we doing this complicated thing? Why don't we just find out the response of y, the output, to x1 a cos omega t plus theta? Because it's much easier to handle an exponential like this here, a e to the power j theta into a j omega t. So let's look into that here. Okay, and similarly, if you were interested in finding y2, the y2 would have been imaginary part of yt here, right? So this is a crucial point. Your interest is in response to, let's say, x1, but what you're saying is find out a response of the circuit to xt, and let's say you find out yt. Then if you're interested in x1, take the real part of yt. That will give you y1t. If your interest is in y2, take the imaginary part of yt. Right? So you will obtain the answer that you're looking for here. Okay, so what we are saying is x1t is what I'm going to apply to my circuit here. We said we're going to analyze our circuit using a sinusoidal signal. So this is what I'm going to apply, and this is what I'm interested in. But what we are saying is, well, what you do is you apply this signal here, a e to the power j theta into a e to the power j omega t. You'll get some response yt, right? And how will you get y1t? Y1t is nothing but real part of yt. Okay, so that's what we are saying. So all this is following from the linearity of the system, the superposition principle, the fact that this is made up of a cosine and sine, and the cosine part is the real part and the sine part is the imaginary part. So when you take the real part here, you get the output that you're looking for, y1t. Okay, so your analysis of this linear system is a linear circuit. So your analysis of linear circuit to a cosine signal like this can be obtained by analyzing the linear circuit to a signal of this kind here, a complex signal of this particular kind. And you will obtain, obviously, when you excite it with a complex signal like this, you'll obtain a complex signal here. But then if you take a real part of it, then that will get you the answer that you're looking for. All right, so that's the motivation for analyzing the circuits using an excitation of this form. All right, so let's continue with this thought here. So we are going to now look at our circuits excited with a signal of this kind here. Okay, theta can be 0, theta can be anything. So if it's a pure cosine, theta is 0. Okay, so now any linear system, any linear circuit that we are talking about can be characterized by a differential equation of this kind here. A ordinary differential equation. Depending on the complexity of the circuit, we may have a third derivative or a fourth derivative. We saw simple RC circuits which had only one single derivative. We also saw in the last lecture we had RLC circuit, we had second derivatives. If I have maybe 3 capacitors in my circuit, maybe I'll have 3 third derivatives. So in general, this linear system will be characterized by this differential equation here. And this differential equation, so the system is characterized by this part here, And this is being driven by an input which is a e to the power j theta into e to the power j omega t here. We're exciting it, this is the input part here. And y is my output part here, right? So this is there. Now it's very easy to show that the solution to this equation will be of this form, yt equal to y naught e to the power j omega t. So when you excite your system with a e to the power j theta into e to the power j omega t, note that this is the only time dependent part. The output is also going to be something here, y0 into e to the power j omega t, right? So the solution is also of this e to the power j omega t form here. And if we substitute it here, so what will happen is each term will have e to the power j omega t, and on the right hand side also we have e to the power j omega t. So e to the power j omega t cancels out, and what we are left with is an. We will take nth derivative here, so we'll get j omega to the power n and so on and so forth. And on the right hand side is a e to the power j theta. So we can find out y0. Y0 would be straightforward. Now note that this is nothing but an algebraic equation in complex variable because we have j there in complex variable. So if we can easily solve out for y0, and therefore we can get an answer that our answer is going to be of the form of y0 e to the power j omega t. So this is very interesting, that if I take a linear system and I excite it with the xt of this particular form, where the time varying part is e to the power j omega t, the output is also going to be of the form e to the power j omega t, but with some y0 here, which is in general going to be some complex quantity here because of j here and all that is here. So y0 is some complex quantity, right? So e to the power j omega t at the input, e to the power j omega t at the output, and in fact every term, every voltage and currents will also have e to the power j omega t. So that part is unchanging, it's there everywhere in my system. Okay, so we have to solve basically an algebraic equation in complex variables here to get the value of y0, and e to the power j omega t I already know, right? So I will be able to get the output here. So the idea is that we take a linear system, we excite it with a e to the power j theta into e to the power j omega t, that's our input. Our output is also going to be y0 into e to the power j omega t. So because e to the power j omega t and e to the power j omega t is there everywhere, you can actually forget about it. It's there everywhere. Note that in this equation, e to the power j omega t will be here, e to the power j omega t will be there in every term, and it just cancels out. Okay, so you don't have to bother about e to the power j omega t. You can just concentrate your attention on this part here. So you can analyze your circuit and you can forget about e to the power j omega t, and you can say, well, suppose the input is a e to the power j theta. Then the response to the output would be some y0, a complex quantity here. And later on, to get the complete output, you can add e to the power j omega t to it, because it's just simply there, right? And this a e to the power j theta is nothing but a complex variable. Sometimes we will write it like this. Sometimes we will write it as a angle theta that you're familiar with in a polar format here. Okay, so this brings us to complex numbers. It shows that the analysis of linear system is basically boiling down to when I excite it by a complex variable here, a e to the power j theta, that's my input. And then the system will produce some output which is also a complex variable here. So just a brief digression, complex numbers you're familiar with. This is what we call as a rectangular form. Let's say 4 plus j3. You can write it in polar form here in terms of magnitude and angle, 5 angle 36.85, which is nothing but this here, 5 e to the power j 36.87. If you write signals, if you have two signals, Z1 is here and Z2 is here, and you want to multiply them together, the amplitudes multiply together, the phase adds up, If you want to divide it up, the amplitudes divide and the phase they subtract. So these are things that you may already be familiar with, and but just to refresh your memories, because we are not talking about complex numbers, these relationships will be helpful for us. So let's see how we can use all that we learned so far. So let's say we have a circuit like this, and the circuit is excited by a cosine, by a sinusoidal signal, which can be expressed as 5 into cos. This is the frequency here, omega t plus 30 degree. And we would like to find out what is current and voltage. But that analysis we'll do a little later on. Right now, suppose somebody has done the analysis and told you that the voltage drop across R is given by this quantity here. 2.5 into cos omega t minus 30. Remember, we said all of them will have the same omega t form here. And so we want to know, so you know the input, you know the voltage drop across the resistor, and you're looking for what is the voltage drop across the inductor. So inductor will be, through Kirchhoff's voltage law, will be Vs minus Vr, obviously. Okay, now how do we solve this problem? Simple problem. All we need to do is subtract two voltages to get the value here. And you could do that. You have two sinusoidal signals and you can subtract and you can get the answer. But what we are saying is the following. We are saying that the cosine signal that you see here, your analysis, your interest is in cosine, but the cosine can be expressed in this form here as the real part of this particular signal here. And the output, whichever output that you're looking for, VL, will be also, when you excite it with e to the power j omega t, will also be of this kind here. Right? So what you do is, this signal here that you see 5 cos 314 can be represented as a signal 5 e to the power j 314.6 t plus 30. So remember what we said? We said excite your circuit through this signal here. Then what will happen is you'll get some output, and the output will be y0 e to the power j omega t. And then what you do is you take the real part of this one, and then you'll get the answer to the real part of this one here. Okay. So now also we said that when you excite it with e to the power j theta into e to the power j omega t, the output will also have e to the power j omega t. So you don't really have to bother about e to the power j omega t. It's there in every term, and that's why it just cancels out, and you can add it up later on. So all that you need to do is focus on this particular part here, e to the power j omega t, just leave it out. So the signal here for us becomes 5 e to the power j 30. Okay, which and similarly VR then becomes 2.5 e to the power minus j 30 here. Right, so focus on Vs and VR written in this form, e to the power j omega t, just forget it. Now perform the algebra, Vs minus Vr. So do that, VL equal to Vs minus Vr. So everything you do with these quantities here, these complex quantities. And so we can do that, Vs minus Vr, we can write this up into complex quantity here, this one into complex quantity, and we get this, we express it back as 4.33 e to the power j60. So this is VL. But now let's do what? Let's add the e to the power j omega t here. Let's add e to the power j omega t here, because it is there as part of all my signals. But you know, we need not write it in every term. We need not write it here. We need not write it here. Everywhere we need not write it. Later on at the end, we add this e to the power j omega t. And remember what our final result is going to be, the real part of this. Okay, so the real part will be cosine part 4.33 cos 314.160 t plus 60 degree here. So the idea is that we had to, instead of working with cosine, we can work with this complex variables here. This complex variables here, and it's much easier to work with complex variables. So the basic idea behind this is the following. We were given two sinusoids, and we were asked to subtract the two sinusoids as a result of KVL to figure out VL. So the strategy is the sinusoidal variables are converted into complex variables here. Vs is 5 e to the power j30, which is written, if you expand it out, is 2.16 minus j125. Vr is going to be 2.5 e to the power j minus 30. Well, if you expand it out, it's this here. So you transform these variables into complex variables. Perform algebra in complex variables. You want to subtract these two quantities, subtract these out, Vs minus Vr. So do that with the complex variables you get here. After you perform the algebra and complex variables, transform complex variable back to sinusoid. So the signal that you're looking for will be this signal here, which can be written as 4.33 into e to the power j60 into e to the power j omega t. Take as real part and you get this here. Right? So you want to work with sinusoids, and what we are saying is work with these complex numbers here. Work with these complex numbers and the analysis become much simpler, and then in the end revert it back to the sinusoid that you're looking for here. So this reminds us of this strategy that we had said in the very beginning in our first lecture, that if you're trying to work a problem, trying to solve it in domain 1, it may happen that the problem, if you transform it into domain 2, it may become easier to solve here, and then you retransform it back here. So for our case here, we are trying to work with sinusoids. We are trying to, let's say, subtract 2 sinusoids. Well, we are saying if you can transform a sinusoid into a complex variable, work with complex, do an algebra and complex variables and transform it back into a sinusoid, that's much easier. Okay, so that's much easier. So this is what we have done. We've basically represented a sinusoid with a complex variable, and we have justified why we are able to get the answer here because of the linearity of the circuit. We have shown that if you take a real part, you'll get the signal back here. Okay, so the idea is that you are interested in analyzing signals, analyzing circuits where let's say the input is of this particular form. So what we do is we analyze circuits in response to signal of this form, Vm e to the power j omega t plus theta here. And we said, you find out response of the circuit to this signal here. Now, this is not a real signal, right? Vm e to the power, it has an imaginary quantity. But as an intermediate step, you analyze the response of the circuit to a signal Vm e to the power j omega t plus theta. And then once you find the response and you take the real value, you'll get the response that you're looking for, okay? And this Vm e to the power j omega t plus theta, because e to the power j omega t is there in every term, basically you can just represent it in the form of, as a short form of this, we say real Vm angle omega t plus theta here. So that's a short form for representation of this. Because omega t is there in every term, we forget about it again in the intermediate steps, and we only look at Vm angle theta here. Right, so if we work with this Vm angle theta, so there's nothing but a complex variable here. And so the idea is you work with this quantity, with this as an input, and similarly outputs also you will get as some complex variable. And you can always transform a complex variable back into the sinusoid that you're looking for. So if you see Vm angle theta, it implies a signal in the circuit of the form of Vm cos omega t plus theta. On the other hand, if you have a signal like this, it implies a complex variable of the form of Vm angle theta here. Okay, so this is what we call as a phasor. This representation of a sinusoidal signal in the form of a complex quantity, complex variable, having the amplitude and this phase part here, theta, is what we call as a phasor here. So Vm angle theta is nothing but Vm e to the power j theta here. So that's the concept of a phasor. So what we are saying is the analysis of a circuit to sinusoidal excitation is basically analyzing the signal in terms of phasors, where the input is cast in the form of phasors, the output is cast, then obtained in the form of a phasor. And anytime you can transform the phasor back to the time domain, the full signal that you're looking for here. Okay, so this is the gist of our argument of phasor analysis. We started with linear system, and we said that linear system obeys superposition principle. So if you know the response to x1 as y1 and response to x2 as y2, then you know the response to a more composite signal a1 x1 plus a2 x2. You can determine it from y1 and y2, a1 y1 plus a2 y2. Then we use that to say, suppose x1 is a cos omega t and x2 is a sin omega t. And therefore, and then we combine them together with an imaginary quantity j here. And then we said that think of a linear system excited through a signal of this form, a e to the power j theta into a j omega t here. And we said if you determine the response to this signal here as yt, then by taking the real part of it, you will get the response to a cos omega t here. Right? So we said analysis of linear system to sinusoidal signal of this form can be transformed into analysis of linear system to exponential signals like this here, a e to the power j theta into a e to the power j omega t. Once you analyze a linear circuit to this signal, then you can just take a real part of it and get back the response that you're looking for. Then we said that when you take a signal of this form, a e to the power j theta into e to the power j omega t, the output is also going to be y0 into e to the power j omega t. So e to the power j omega t is there everywhere, and you can temporarily forget about it. And therefore, you can then just think about characterizing your system in terms of a e to the power j theta, and then you calculate this response in terms of y0 here. And then later on, transform it back into the signal that is of your interest. You can go back to, so once you work in terms of a e to the power j theta, which we call as a phasor. You'll find out the response of the output in terms of y0, and then add e to the power j omega t to it, and take the real part of it, and you'll get the response to a cos omega t plus theta here. So that's the basic idea behind phasor analysis, that sinusoidal analysis is being reduced to basically analyzing the linear system, the linear circuit in terms of complex variables here. So the input is represented as a complex variable here. The output is also a complex variable here. So in the next lecture, we'll see how each one of those elements that are there, R, C, and L, and all that, they can also be transformed into a complex element with a complex value here. And then the circuit can be analyzed in terms of those complex variables, in terms of these phasors, and the phasors can be transformed back into time domain anytime we want, okay, through by adding e to the power j omega t and taking the real value. All right, so let's stop here.